Do you need the slide set up, or are you switching to chalk today?
Yeah, I'm okay. Switching to chalk.
It says I have 1 minute.
Okay.
It's right on time. Ready?
Yeah, sure.
So it's my pleasure to introduce Martin Leguil, who will talk from the University of Picardie, who will talk about ergodicity of conservative and also of diffeomorphisms.
Thank you very much, John. Hello, everybody. So today I'm going to continue in the direction of ergodicity. So yesterday, just to recall, so we detailed the proof of the stable manifold theorem and the absolute continuity of invariant foliations, so stable and unstable. And today we are going to use it to show something about ergodicity. So I will first speak about the conservative case, and then also try to say what's the natural replacement for volume when the system is dissipative. Okay, so let me start with the first result I want to present. So it's a theorem by Hopf and Sinai that says that if F is C2 conservative another diffeomorphism, so conservative, just trying to be consistent with my notations of yesterday, was denoting by M usually the remaining volume. So let's assume that you have a remaining volume M which is preserved by the dynamics, and if the manifold is compact connected, then F is ergodic. So it's this ergodicity result which I first want to discuss. And actually, the proof uses the strategy first introduced by Hopf, that I think John already mentioned. And that's also going to be useful for the second part, for the dissipative case. So let's first see in this conservative setting. So this argument goes as follows. So let's fix phi, a test function in L2, and let phi f bar to be the lim sup of the temporal averages of f by the dynamics in the future. So we take the lim sup as n goes to infinity of those block of averages. Okay, so by Birkhoff theorem, we have some characterization of this this guy. So actually, phi f bar is the projection of phi on the space of invariant functions. So this projection from L2 to L2, what I denote by L2F, which is the set of functions psi in L2, which are invariant by the dynamics. Okay, so we have this lim sup is just the projection of the space of invariant functions of the test function we started with. Okay, so now the claim is to show ergodicity it's enough to show that for any continuous test function corresponding projection is constant almost everywhere. Okay, and in fact, in that case, it's going to be equal to the average of this test function. So why is it enough to show that for continuous functions? It's just essentially the fact that the projection is continuous, and the fact that the test functions which are continuous is dense in L2. So in that case, it will be implied that the projection of L2 the projection of L2 is going to be just the same as the constant functions. Okay, so that proves ergodicity. So in the following, for the argument introduced by Hopf, we need continuity. Is why we have this reduction here. Okay, so let's continue. So the proof goes as follows. Basically, the first thing is to show local ergodicity and then globalize the argument. So for local ergodicity, so let's fix the test function which is continuous. So now we still have to consider them. And the thing is that we show that it is actually locally constant. Okay, so the key ingredients behind Hopf's argument are the following 3 points. So first point is that this limb soup is constant among the leaves of the stable foliation. Okay, so why is it so? It's just the basic remark that when we average with respect to the dynamics in the future, for 2 points which are in the same stable manifold, so say y is in the same stable manifold as x, then so by definition we know that they are going to get closer and closer in the future. So this limit is 0, and then we average essentially the same quantities as when k is very large, by continuity of phi. So it's why we need continuity when I started. Okay, and so essentially then it's just a consequence of Chizaro's theorem. Okay, so that's the first key point, that we have this constancy along the leaves of WS. Then second point is of different nature, just saying that when I consider forward temporal averages, it's actually almost everywhere the same as backward temporal averages. So it's why I kept this index f, that I mean when we go backwards, so when we average this test function with respect to past dynamics, then we get almost the same almost everywhere. And why is it so? Is because, as we saw, this is just the projection of phi in the space of f invariant function. But being f invariant is the same as being f minus 1 invariant. Okay, so projection on the space is the same as projection on the corresponding space for f minus 1. So that's the second point. And the third point is the dual version of the first point, that when you look at backward averages, then they are constant along the leaves of the unstable foliation. Okay, so it's the combination of these 3 arguments which are behind Hopf argument. And so now let's see how the proof goes. And one technical point is precisely related to absolute continuity of the foliations, which we detailed yesterday. So let me show how to conclude. So let me introduce the measurable set A, where those two functions, two averages as in point 2 are equal. Okay. So by what we observed, it's full measure set. Okay. Now let's fix delta small enough such that U, which is just the saturation So what I do is just I take an unstable disk and I saturate by local stable leaves. Okay, so this delta just means that we look at delta neighborhoods of these points within their stable and unstable leaves. Okay, so we take this saturation of this small unstable disk by the corresponding stable leaves, and then by local product structure, we know that if delta is small enough, then this set is going to be the homomorphic image of basically minus delta delta to the dimension of the unstable space times minus delta to delta times the dimension of the stable space. Okay? So that's just what comes from local product structure. So now that we have introduced these things, absolute continuity of W tells you that for almost every x in M, M so let me write. So for M almost every x in M, the leafwise measure of the bad set, so the complement of A is this bad set where we don't have this coincidence of the two projections. So this bad set intersected with the leaf, the unstable leaf, has zero measure. Okay, it's just coming from absolute continuity. We have this bad set which is of zero measure, which you are looking at along the leaves. Okay, so is a zero set which you are looking at on each of the leaves, and for a typical leaf, it has also zero measure on the leaf by absolute continuity. Okay, so it's one first point where we have essential need of absolute continuity of the unstable foliation. Okay, so that's the thing, and so now let's continue, and the idea is to show that when we saturate, we still have we still give zero weight to the bad set. Okay, and now we are using transverse absolute continuity of stable foliation now. To show that when we take the union over all points y in the bad set intersected with a good unstable leaf, and that we saturate with local stable leaves, then we get zero. Why? It's because so now we picked a good x such that we have this property. Okay, so that would be x and the leafwise measure of the bad set on this leaf is 0. Okay, and what we are doing is just saturate this small disk with leaves of the stable foliation. And absolute continuity tells you that if you take smooth foliation which extends the unstable foliation, then for almost every transversal, then the volume, the measure of the intersection of the leaves starting from the bad set with this transversal is going to have zero measure. Okay, so then just almost all those red leaves is going to give zero measure to the bad set, and then just integrating over all of them, you get that property. Okay, then you use absolute continuity of stable foliation. Okay, so now we are almost done. Okay, so in other words, if I define, since I define this set U, okay, so the collection of the saturations of stable saturations of the points in the unstable disk of X, then what it tells me is that the union over all Y in the good set intersected with unstable disk of X. So this set is going to be have same measure as the set U we started with, okay? Because we just saw that the complement has zero measure. Okay, so now let's study what's happening for points in that set. Okay, and so let Z be a point here. So in other words, we have Z belongs to the stable disk of a point Y in A intersected with the unstable disk of X. And then let's look at the value of this function phi bar at Z. Okay, so just maybe let me draw a picture. So what we are doing is the following. So we have X, we have the small unstable disk of X, we pick a point Y in A in this unstable disk, and then we pick a point Z in the stable disk of Y. Okay, so that's the picture. So Z and Y belong to the same stable leaf. So by the first property which we saw in the remarks related to Hopf argument, so this is going to be the same as the value of the function at Y. Okay, because they are stably connected. Now we picked Y in the good set where forward and backward averages coincide. Okay. So the fact that Y belongs to A ensures that we also have that. Okay. And last step of the argument is Y and X are unstably connected. And since I'm looking backwards, it's also the same by property 3 above. So that is the same as this. Okay. So now we are done, because so what we just saw is that so we have this neighborhood of X, okay, which is this coming from the local product structure. This neighborhood has the same measure as this set, and any point in that set has the same value for this phi bar function as that guy. Okay, so it does mean that phi f bar is constant almost everywhere, m almost everywhere on U. Okay. So this concludes the part about local ergodicity. Okay? It's okay? Okay, so we see that, I mean, roughly speaking, the argument is we have the idea is just using constantly along stable leaves and unstable leaves, and by transversality of those two foliations, we show that locally, we expect that locally we have a constancy, just moving along the leaves of those two things. There's just this technicality that we need to deal with this set A of full measure, where those two things coincide to make the bridge between what's happening forward and backwards. And that's where we need absolute continuity of the foliations. Okay, so that's how we get local ergodicity. Now, how to conclude about ergodicity globally? So, from what we have just done, so we have seen that for any x, there exists ux, a neighborhood of x, where phi f bar is and almost everywhere constant. Okay, so we have this neighborhood ux, and then to conclude is just a connectedness argument. M almost everywhere, just covering the space with such neighborhoods where the function is locally constant. Okay, so then we do have concluded ergodicity of our map. Okay, so that's basically the Hopf argument for conservative unresolved diffeomorphisms. Now, in the remaining time, what I would like to explain is how it goes in the hyperbolic case, but dissipative case. So what's the natural replacement?
You make a remark that the same proof proves K property.
Yeah, exactly. Yeah, I didn't insist on that, but it's stronger. Yeah. What we can do is we can prove K property, and and same actually in what we are going to do now. So now let me speak about Sinner-Bohen measures, which usually are abbreviated as SRB. And those are the good guys which were introduced to explain the statistics on a hyperbolic attractor, transitive, in a coherent way with respect to volume. Basically, when volume is not itself invariant. Okay, so the thing is that even though volume is not invariant, there is still a way to describe the statistics of a large set of points. And what do I mean by large is Lebesgue large. This set should have positive Lebesgue measure. Okay, so the definition of SRB. So SRB, as I was mentioning, is from Sinner-Bohen. I think the strange order is just comes from the fact that it was first work of scenario and then real point. But so if you have mu and F invariant Borel probability measure, we say that mu is SRB if for every size measurable partition subordinate to W, U, the conditional measures or the disintegration are AC with respect to the Lebesgue measure on the leaves. So what's the picture? It's basically, so for example, we can take a foliation box for the unstable foliation and look at the disintegrations. So say this is psi, and subordinate just means that, I mean, we have some additional properties, but basically it's just a small part of unstable manifold. Okay, so what we can do in such a partition is we disintegrate our measure, and on each such leaf, so we have two measures which live naturally there, is the disintegration and also the restriction of volume to this leaf. Okay, and it's SRB when there's discompatibility between the two. So we have the following proposition. So I'm not going to completely detail it because it's going to be essentially the same arguments as those that I'm going to explain afterwards. But in connection with what I was mentioning yesterday, so physical measures are those for which we have an open set where M, almost every point in this open set, follow the statistics of the measure. So it's the type of measure you can observe if you pick a point at random and you follow its forward object. Okay, so one nice thing is that these SRB measures are directly related with a physical measure in this hyperbolic set, in this hyperbolic setting. That so ergodicity and SRB implies physical. So the two ingredients behind this are essentially the Hopf theorem plus absolute continuity of the foliations. So let me just detail a bit, but as I was saying, we are going to see that in more detail. So Hopf tells you that the basin of the measure mu by ergodicity it has full measure. Okay, so mu, almost every point follows the statistics of mu. And now, so we know that for a typical unstable disk, so say a small disk here, almost mu, u, almost every point there is going to be in the basin. So we disintegrate our measure with respect to unstable disks. So say mu u x, almost every point there is going to be in the basin. By mu u, I just mean the unstable conditional measure of mu on this disk. Okay, so for a typical disk, we have that, but then by SRB property, we also know that in that case, MWU, almost every point is going to be in the basin. we can go from that to that just by the SRB. Okay, so M almost every point there is good, in the sense that it follows the statistics of mu, and then same thing as in Hopf argument, we saturate by leaves of the stable foliation, and then absolute continuity so say this product structure set is denoted by U. So absolute continuity of WS tells you that M, almost every point Z in U is in the basin. Okay, because points Z. So for MWUX almost every Y, we follow the statistics of mu, but points Z in the same stable leaf as Y follow the same statistic as Y. So they are also in the basin of mu. And by absolute continuity, because there we started with full measure set for Lebesgue measure, the set we produce by saturating by stable leaves is also full Lebesgue measure. Okay, so this shows that M almost every point in this neighborhood follows the statistic of mu, which is a physical property of that measure. Okay, so that's one key link between SRB property and physical measures. And so the second main result I wanted to present today is the result by scenario Verne for hyperbolic attractor. So let's consider lambda a transitive attractor, hyperbolic attractor, of a C2 diffeo F, then there exists a unique F invariant Borel probability measure on the attractor, such that for any test function phi, and for M almost every x, so M is still this Lebesgue, this Riemannian volume, then it holds the following, that the temporal averages are going to converge to spatial average with respect to mu. And equivalently, in fact, mu has SRB property. Moreover, the system F mu is ergodic. And as Felix was mentioning, in fact, you can also here say more that you have when the attractor is topologically mixing. In fact, it also implies a K property. It's stronger than that in some cases, but I'm going to focus only on ergodicity. Okay, so it tells you that for a transitive partially hyperbolic, transitive hyperbolic attractor, you have a natural replacement for volume, which is this SRB measure, and so we are going to construct it and to show this ergodicity property. Okay, and then to conclude about physicality, it's essentially following from what I was just mentioning before. Once you have ergodicity plus SRB, then you have this physical property. Okay, so in the remaining term, I'm trying to give the outline of the proof. So let's start. So first, let's construct this candidate measure mu. So the construction is dynamical. And at the same time, you are going to show that this measure which you produce has the SRV property. So for that, let's pick, just for definition of what I mean by, I want to do something called the canonical neighborhood. So let's pick some stable disk for delta small. Okay, so small stable disk, and let U be the saturation, exactly as what we did previously. But in the opposite direction. So we start with some stable disk. And we saturate by small unstable disk. Okay, so the set which we produce here is going to be this U. Okay, so just such set in the following we refer to them as canonical neighborhoods. Okay, so that's just for a definition of that. So now let's see how to construct the measure mu. Let's fix a point x naught in lambda and consider the small unstable disk around x naught. And the measure we start with is just the Riemannian volume carried by the leaf normalized. So we just normalize to make it probability measure. Okay, so the construction goes as follows: we are going to push this unstable disk and consider the measures, the push forwards of this measure mu naught. So for k positive, let's consider the measure mu k, which is the push forward after k steps of mu naught, and this measure is going to live on FKL. Okay, and so you have basically the following picture. So we start with a small unstable disk L. Okay, and we push it by the lines. And as we push it, it's going to get longer and longer and go to pretty much everywhere in the attractor. So after k iterations, it's going to be roughly like that. And so the observation is that for any U canonical neighborhood as I was introducing, let's consider UK to be the union over all this d alpha. So just for simplicity of the notation, when you have this canonical neighborhood, instead of carrying all these things, I'm just going to denote by d alpha the small disk in this canonical neighborhood. So let's consider UK to be the subset of U, which consists of all the small disks which are completely contained in Fk of L. Okay, so it's basically the following picture. So we have our very, very long image of the unstable disk, and we pick a canonical neighborhood U, and maybe some of the disks are doing like that, but I don't know. Maybe this disk is bad, that it doesn't meet completely but still as if we start with a point which is not too close to the boundary of the initial disk, then the typical thing which we see is that one. So most of the disks are going to be actually in UK. Okay, so then let me denote by mu hat k the indicator function of this UK times the measure mu k. So mu k was this push forward, just restricted to the disks which are good. Okay, and since most disks are going to be good, in fact, what we see is that when k goes to infinity, the difference between those two functions, mu k and mu k hat, is going to go to 0. Okay. Now, so just to summarize, we start with a small disk. We take the normalized Lebesgue measure on this disk. We push it by the dynamics, and we here we just want to look at good disks. And to produce our measure mu, so what should be the candidate for the SRB measure, we take an accumulation point of the averages of these measures. Okay, so because of this averaging, the thing which you are going to get taking an accumulation point is invariant. It's going to be a probability measure also because all of them are. And the thing is that, in fact, for any canonical neighborhood U, what you do, I mean, if you do this thing that we only look at the measure on the good disks, when you consider mu hat instead of mu, then it's also going to converge to the same accumulation point. Okay? Just this remark that it doesn't matter if we forget about bad disks. Okay, so now to get the SRB property, I'm not going to have time completely to explain that, but it comes essentially from uniform expansion along the leaves of W. So so it's uniformly expanding plus as uniformly bounded C2 derivatives. Then we can do some distortion argument. And at that point it's important to have C2 and not C1. So it's the key thing. Then we can compare in a uniform way the radon Nicodim derivatives of the mu k with the Riemannian volume carried by the leaf. So it's the following. uniform bound. So, as I was mentioning yesterday, for all finite iterations, the measure which we get is always going to be in the same class as these volumes. Okay, and the point here is that you have a uniform bound on the Radon-Nikodym derivative. Okay, so this bound doesn't depend on k. Okay, so that's the main point. And in particular, this bound also works for the average so for the average and also independently on n. Okay, independently of which step we consider, and then this bound also propagates to the accumulation point, which we chose from. So that says that nu is SR. So there is it's not completely detailed, but the argument is really a distortion argument. Essentially, saying that when we look at the measure on the unstable disk, going backwards, the points are going to have the same type of behavior, and I mean, what we see at different points in the same unstable disk is not changing too much. Okay, so that's basically the construction. So we start with unstable disk, we push it, we look at averages of these push-forward measures, we take an accumulation point, and by this distortion argument, you have a uniform bound. It guarantees that the limit measure is going to have SRB property.
So you didn't use Markov partition?
No.
I thought I remember it is senile.
So sorry?
I think it is how senile.
Yeah, it's I think it's Sinai and also Sinai Pessin later, maybe.
Pessin and
Yeah, yeah, exactly. Yeah, maybe Sinai Pessin, it was for partially hyperbolic case, but still it's same argument. So we have this measure which has SRB property. So now I'll try to conclude about how we show ergodicity of the measure which we produced and how it relates to the physical property. Okay, so for that, let me just give a definition. So given nu in MF, so that was how I was denoting yesterday the set of invariant measures, Borel probability invariant measures for F. We say that the point X is future generic if it is in the basin of the measure nu, as I was introducing yesterday, but which means that for continuous functions phi, forward averages of phi with respect to the dynamics starting at x is going to converge to special average with respect to nu. Okay? So it's what I mean by future generic, the points which follow the statistics of nu in the future. Okay? So, in the same way, we can say that it's past generic so if you have the same property for f minus 1, so if we go backwards and do these temporal averages, and it's generic if it is future and past generic. Okay, so that's just a definition. Now, since we don't know a priori about ergodicity and so on, so the thing is to consider ergodic decomposition. So let me just recall what that is. So if you denote by EF the set of ergodic F invariant Borel probability measure, then for any mu in MF, so the set of Borel F invariant probability measure, but not necessarily ergodic, no? There exists a Borel probability measure tau nu on the space of ergodic measures such that nu is the average of ergodic measures with respect to this measure tau nu. So it's basically we can decompose our F invariant measure into a combination of ergodic measures. Okay, so this in particular tells you by Birkhoff theorem that nu almost every point x is generic with respect to some ergodic measure depending on the point. Okay, and that's coming from Birkhoff. Okay, just if the measure we start with is not ergodic, not all the points, not necessarily all nu, almost all the points are going to follow the statistic of nu, but still they are going to follow the statistic of one ergodic component of nu. Okay, so but this may depend on x. So just for the following, I'm going to abbreviate this set as G nu. It's not very nice in the sense that it looks like generic points for nu, but it's just the set of points which follow the statistics of one ergodic component of the measure nu. So that's just some facts. So now let's conclude the proof of the result of Sinai-Riad-Bowen. So first, mostly about ergodicity of the measure mu which we produced. So it's why I presented first the Hopf argument in the standard conservative case, because the proof is going to follow the same type of idea. It's just slightly more complicated. So first, as in Hopf argument, we show local ergodicity for the system F nu. And in fact, looking at that, ergodicity can be interpreted as the fact that nu, almost all the points are generic with respect to the same measure. Okay? So it's essentially what you are going to check, that there is locally unique, a measure nu which, with respect to which almost every point locally is going to follow the statistics of nu. So for any density point x of the measure mu which we constructed, there exists V neighborhood of x and nu depending on x, such that first, so it's what we want to show, is those two properties, nu almost every point z in this neighborhood is future generic with respect to nu. Okay, so this measure nu may depend on x, but just locally it will be the same measure for everybody. And m, now almost every point z in that set is future generic with respect to mu. Okay, so it's the two properties which we want to show to get some local ergodicity. So it's indeed local ergodicity in the sense that here we kill the dependence with respect to the point locally. And that is a variation of Hopf argument. So let's consider U a canonical neighborhood centered at X. So something like that. We disintegrate mu with respect to disks in U, and we pick one of them such that you have two properties. So first, it's not too far to x, from x, sorry. So it means that x belongs to the neighborhood V, which is the saturation of this small disk W0 by a stable leaf. And the second point, M W0 almost every y is generic with respect to some m mu y. Okay, so let me just. So the first point is just saying that when you saturate by so say this one is our nice transversal, and when we look at small saturated disk, then X is still going to be somewhere in this saturation. And the second point is saying the following, that M W naught almost every y is generic with respect to some M mu y. So why is it possible? It's coming from the SRB property. So let me explain. So as we saw in the previous remark coming from Berkhoff, is that mu almost every point is generic with respect to some measure mu y. Okay, but so it means in particular this set G mu, which I denoted there, as full measure. Okay, and this full measure set, when we disintegrate it on this canonical neighborhood, it will have full measure for the disintegrations of mu. Okay? So first we use mu, but now once we have the disintegration giving full measure to this G mu set, then we also know that for the Lebesgue measure because of the SRB property which we have. Okay, so so we let such a good W naught, so with this property, and that M W naught almost every point is going to be generic with respect to some mu y. So then the next part is just following Hopf argument and noticing some invariance, I mean constancy of this mu y along dynamical leaves, basically. So if you look at y prime in W not intersected with G mu. Since they belong to the same unstable leaf, so backwards they are going to get closer and closer, which says that so if both were generic with respect to some measure mu y prime initially, in fact they are generic with respect to the same measure mu, which is the same as mu y prime. Okay, so because both were in this good set, they are generic with respect to one of those two measures, but because they go in the closer and closer backwards, in fact they are generic with respect to the same measure. So those two measures coincide. So we have a local constancy on this unstable disk. So similarly, any point z in V nu, so what is V nu? V nu is the saturation of W0 intersected with G mu of WS disks. Okay, so from the first part, because y prime are in the same unstable disk, you have matching of the corresponding measures, but if we saturate by stable disks are going to follow the same statistics as points where they are based on the disk. So Z is going to be future generic with respect to the same measure as Y. Okay, and so it's essentially the same as Hopf. But now we remember that the set we started with as full measure, so mu W naught gives full measure to points in G mu, and WS is transversally absolutely continuous. So we conclude that for all unstable disks d alpha in our canonical neighborhood, the volume measure restricted to that leaf gives full measure to V nu. Okay, so in other words, V is the set. When we forget about G mu, V is going to be this set which we produce here, and it's going to be of same measure as the set V nu, where points follow the statistic given by nu. And okay, so we have that property. So that's for the Lebesgue, the remaining volume on the leaf. But now we want to go back to mu, and that comes from SRB properties that we can pass by that property to the conditionals of mu. So for mu, almost every such disk, the conditional measures on d alpha going to give full weight to V nu. Okay, so I'm almost done, and
You've gone 3 minutes over. Maybe you can just wrap up in words.
yeah, sure. Yeah, it's so yeah. Let me just finish. So. As I was saying, so SRB property tells you that, so we can have this property back to the disintegrations of mu, and then in fact this V nu has same measure as V. So it means that V nu, which are the points following the same statistic as nu, has full measure in V, this neighborhood. So they all, almost every point for mu follow the statistic of the same measure, so we do get this local ergodicity. Okay, and in fact, the same can be done for the Riemannian volume. So we get this local ergodicity. Now, just two words. So what remains? So we have local ergodicity. To conclude global ergodicity, we have this local ergodicity saying that for small neighborhoods, you have constantness of this measure with respect to which we are generic. But if you take another such neighborhood, we can go from one to the other just by transitivity, which means that the measures on the two sets are going to be the same. So we have a global measure with respect to which we are generic. And as I was saying, this shows that the system is ergodic. Okay? And final point is that once you have ergodicity plus SRB, then it's the consequence of the previous arguments which I was mentioning that we do get physicality, which was the last point. Okay? So thank you very much and sorry for being over time.
Are there any questions? Well, let's thank Martin again. We will be back at 11:30.